Welcome back to Statics. This is ENGR 214 ampersand Bellingham Technical College Winter 2020. And we are continuing with our discussions about shear and bending moment. And we're going to go on to another example. Pretty similar to our first example, a little bit different constants. Simply supported beam here with a hinge at A and a roller support at B. So three forces that can be applied at the supports. We have a single point load at x equals 2 feet. We have a point couple of 40 foot-pounds being applied at x equals 4 feet, and then we have a distributed load of 10 pounds per foot being applied between x equals 4 feet and the end of the beam at 8 feet. So the total beam length is 2 and 2 and 4 is 8. So before we continue, we're going to do a quick review of the integral relationships, and we're going to look at our distributed load being directed downward and have a little bit better picture than we did in the previous lecture. I got to apologize for the one that was drawn with the conditions of equilibrium on the beam element that was not visible. This one's visible, so it's worth giving a quickie review. So we've taken a beam, a section of it that's delta x wide. We've hacked off the whole beam to the right, and we've hacked off the whole beam to the left. We've defined 2 points on the faces of the hacked off sections. We've assumed that this remaining section, or in fact the whole beam, had negligible height and negligible breadth in the direction outside of the paper. So it's really only the x direction that matters. And so we've represented the shear and the bending. We're kind of going to discount axial forces for the moment. Those are pretty straightforward. We're more concerned with the shear and bending relationships now. So we're going to represent the shear forces being exerted on this element by the right-hand side that was cut off as our shear force at x plus delta x, and our bending going in the counterclockwise direction as m at x plus delta x. Point R is x plus delta x referenced to some x equals 0 way over here at the left, and point Q is at point X. And so the left-hand side of the beam that we've cut off at cut face Q here is exerting a force V at X downward at point Q, and it's exerting a moment of M at X going clockwise. And we have our distributed load again, and it's being applied over the whole beam, but we're only concerned with the part that's being applied over our section delta X. It has a value of Q as a function of X. We don't know what the function is, but we do know that it has an average value of Q1 over this section from X to X plus delta X. This is an average value. And that average value is assumed at a point that is equal to X plus this little squiggly delta again. So we'll revisit our mean value theorem in evaluating the significance of x sub 1, q sub 1 and delta for our moment and our total sum of the forces in the y. Okay, so we'll apply our conditions of equilibrium to this little element again. And here's the sum of the forces in the y. We have negative v sub x. We have negative average value of the distributed load times the width. So that effectively, that is the definition of average value from the mean value theorem. This is taking the place of integrating q sub x from q to r with respect to x. And then we've got an upward force of v at x plus delta x. So there's our sum of the forces in the y. And we can do some algebra again. We can move this term over to that side and then divide everything by delta x. And this time, having defined q as being in the downward direction, downward applied distributed load, which we'll be encountering most of the time, we end up with an expression of what's going to be the definition of derivative equaling the average value of our distributed load. And then as we take the limit of both sides as delta x approaches 0, we get dv dx equals q of x. So we've dropped the negative sign versus the last derivation simply by presuming that our distributed load is downward. Okay, typical sign convention. Okay, we're going to do the same thing with moments, and we can just add them up again. We have positive moment about q. This time again we're going to take the moments about q, so it's the other side of the volume element or the beam element. So we have negative m sub x, we have positive m at x plus delta x, and now this is the shear force that's going to exert a moment. This one is now coincident with the point we're taking the moment about, so we're going to have this times delta x in the positive direction, positive moment, and then we're going to have a negative moment due to our distributed load. So we see that reflected in our sum of the moments. Again, we have positive delta x times our shear force over on the R face minus the position of our resultant average load from the distributed load. So Q sub 1, which is the average value of the load distribution in like newtons per meter, times the total width of our beam element gives us the equivalent force, and then that little delta here is the position by default of that resultant. So we're going to do algebra again, move everything that doesn't have an m in it, which is this term and this term, over to this side. This acquires a negative sign by moving over. This stays positive. We divide the delta x over to here. We notice that that is the definition of the derivative of moment with respect to x, and we make that a true derivative by shrinking delta x down to 0. And when delta x goes to 0 in here, the shear at x plus delta x approaches the shear at x, because we effectively move this point infinitely close to that point. And in so doing, we squeeze this delta down to 0 even faster. So you can really see that squeeze theorem working to make this equal to 0 as we shrink delta x down to 0. So we're left with our first derivative of the moment with respect to x equaling negative shear force. And so notice we still got the negative sign even though we took the moments about the other face using our sign conventions. Okay, having given ourselves a little refresher, now we're going to start applying this to problems. We're going to start with this particular example, and we're going to use some definite integrals and make those handshakes a little bit easier than it was in the previous problem. So we're going to start with the support reactions. Again, we're going to have to get a resultant position and load for our 10 pounds per foot distributed load, which is pretty easy because it's constant. So that's going to end up being 10 pounds per foot times 4 feet applied dead center, and then we just simply sum forces and moments, not forgetting that we've got a point moment to add to the mix, and we get a sub y plus b sub y plus our 30-pound applied load minus our 20-pound resultant of our distributed load equals 0, and then we're going to sum the moments about a. So we'll get 30 pounds times 2 feet positive plus b sub y times 8 feet minus our resultant of our distributed load at 6 feet times 40 pounds, which is what it was, and then somewhere in here we should have a 40-pound applied moment right here. So we sum that to 0 and we can solve for b sub y and then plug that back into here and get a sub y. So we have a negative 7.5 pounds being applied by that leftmost hinge. So that's going to be a change in sign of our shear force that's going to be applied from the rest of the beam, because if the hinge is pulling downwards, when we open that cut face, the remainder of the beam is going to have to be pulling upwards on it. And then the support load at B sub y is pushing up with 17.5 pounds. Okay, so we're going to look at one section from the hinge to the 30-pound point load, another section from that point load to the beginning of the distributed load and the picking up of the point moment, and then on out to the end of the beam. So we're going to start with our x greater than or equal to 0 and less than 2 feet. The distributed load is 0, which is equal to dv dx. And so we can write that in differential form as dv equals 0. Now I'm going to take this differential form and I'm going to integrate it. So I'm going to write an integral from v at 0 to v at x. This is not the same as x equals 0. This is the shear force when x equals 0 to the shear force when x equals whatever x with respect to v. That's going to be equal to the integral of this constant over here. But let's evaluate this side first, assuming it was 0 on that side. So we end up with just putting these limits in. We can use, this is I think the fundamental theorem of calculus, where you can say that if you have an integral with respect to itself, you just end up getting the function evaluated at the limits of integration, which we do. So we end up with the function at x minus the function at 0 equals 0, which we'd set it up for, dividing one side by dx. So the shear force at any x is equal to the shear force at 0. Well, the support reaction is negative 7.5 pounds. So the shear force at 0 has to be 7.5 pounds to balance, or that tiny bit of beam would start accelerating downwards. So the shear force anywhere is 7.5 pounds. So if we take that expression as v sub x equals a constant, we can set it equal to the negative of the first derivative with respect to x of the moment. And we're going to treat it the same way here. So we're going to write it in differential form. So we'll say dm, and we're going to bring the negative sign over to the other side. So we're going to say dm, which is a function of x, is equal to negative 7.5 pounds dx. This is basically the same as this expression, except differential form rather than derivative form. They're totally equivalent, but it makes it much easier to set up a definite integral. So I can integrate the left-hand side from the moment at 0 to the moment anywhere, and I can integrate the other side from x equals 0 to x equal any x. So again, dropping in the limits of integration and using the theorem of integral calculus, I can replace this with just the function at its limits. So I have the moment anywhere minus the moment at 0 is going to equal negative 7.5 pounds times x, evaluated between x equals 0 and x. Well, the moment at 0 is 0 because the support reaction can't supply it. We had a hinge there. So I can evaluate this right-hand side at x and at 0, and I end up, if I put in 0, I end up with just negative 7.5 pounds times x. So I can say, since m at 0 is 0 and this side at 0 is 0, I'm left with just the moment at any x is equal to negative 7.5 pounds times x. I can evaluate this at x equal 2 feet, and I can get a negative 15 foot-pounds for the moment. And of course my shear force anywhere is 7.5 pounds. Okay, and this will pop into my next section. So now I'm gonna put myself anywhere between 2 feet and 4 feet including the 2-foot limit, which has my 30-pound point load. Q sub x is still 0. So V sub x is going to be a constant, and I can evaluate that without doing an integral, just simply by saying V sub x is a constant everywhere and applying the conditions of equilibrium and saying, well, V sub x is the only thing left in the y direction, so 30 pounds upward minus 7.5 pounds downward means I have a net applied 22.5 pounds upward, so V's got to be pulling downward. So as I cross that 30-pound load point, the shear force being applied by the beam that I cut off on the right-hand side switched from being 7.5 pounds positive to being 22.5 pounds in the negative direction. So it took a step function down. Okay, I have a number. Now I want to know something for shear. Now I want to know something about moment. So I can invoke my dm dx equals negative v sub x, which is equal to positive 22.5 pounds. Again, I can write this in differential form, so I can say dm equals negative v sub x dx, then just integrate. And this time I'm going to integrate according to limits rather than throwing out a constant. So I'm going to integrate from 2 feet to any x on both sides. So I'm going to go from the moment at 2 feet to the moment anywhere, and I'm going to integrate this side from x equals 2 feet to x equals any x, and go ahead. So I look at the moment at x, it's whatever, minus the moment, actually it'll be a function which we're going to establish, minus the moment at 2 feet, and that was my negative 15 foot-pounds from previous. So I drop that right in. So m at x minus a negative 15 foot-pounds is the same as saying m at x plus 15 foot-pounds. Now I have a positive, what's ending up being, here's our 2 negative signs, a positive 22 foot-pounds. Going to integrate that. Gives me 22.5 pounds times x. So that's the integral of what's in here. And now I'm going to use my limits of integration from 2 to x. So that gives me 22 pounds times x minus 22.5 pounds x minus 22.5 pounds times 2 feet. So I get something that's in foot-pounds, gather all the constants together, and I get an expression for moment as a function of x at any x in this interval equals 22.5 pounds times x minus 60 foot-pounds. So as I pass this point, shear switches. Let's see what happened to moment as I went from one region to another. So in my first region, moment had a negative sign, shear had a positive sign, moment was linear with x but headed downward. I passed my 30-pound applied load, my shear took a step function downward, and the slope of my moment equation with x, which it's still linear, but it went from negative to positive, switched. Okay, our next segment now is past the 40 foot-pound applied moment, and we're picking up the distributed load. So at 4 feet, Q is still 0 right at 4 feet. We haven't quite picked it up yet. V is still negative 22.5 pounds from the previous section, and if we evaluate this at 4 feet, we get 30 foot-pounds. So those are our initial left-handmost conditions of our right-handmost section, here from 4 feet to 8 feet. So we're going to use this set of conditions to evaluate at that leftmost limit. Okay, so now we have a distributed load. Q sub x equals 10 pounds per foot. So we can write that in terms of our dv dx equals q of x, write that in differential form. So dv equals q of x dx. Integrate both sides and you're here. So the shear at 4 feet, the shear at any x, we have x equals 4 feet, x equals x, and here's our shear expression, or excuse me, our distributed load expression. Take the integral of both sides. So v at x minus v at 4 feet, which we can drop in, equals 10 pounds per foot times x, so we just evaluate the integral, and then we're subtracting the integral evaluated at the lower limit of integration, which ends up being 40 pounds. So the shear force exerted by the remaining right-hand member of the beam at any x on this interval is going to be, and we do some algebra to pool our constants together and drop in our negative 22.5 pounds from the previous segment to evaluate v at 4 feet. We get v at any x in that interval being 10 pounds per foot x minus 62.5 pounds. So now, rather than being a constant, we have x being a linear, or excuse me, rather than having shear being a constant, shear is now a linear function of x, pointing upward as we go to higher x's. And if we want to pop in an x equals 8 feet, we do get a value of 17.5, which is consistent with a support, rather than a v of 17.5 pounds being applied by a cut-off portion of the beam on the right. It's being applied by the right-hand support, which is a good sign. That means we're pretty much correct all the way up to this point, and we only need to apply correct manipulation to this particular expression to get moment, and we're done. So we can go back again to our relationship between moment and shear and say the first derivative of moment with respect to x is equal to negative of the shear function with x. Go to a differential form. dm equals negative v of x dx, and then use this expression for v at x. Write our integrals, evaluate our integrals, and again, the moment at 4 feet, we're going to go back to our previous segment where we evaluated this at x equals 4 feet and got 30 foot-pounds, and in it goes here. And then we evaluate this integral, taking the integral with respect to x and putting in our x-based limits of integration. But we have to do something else to this side before we get over to that side. We had a point moment. So the moment at just shy of 4 feet, we could call it 4 feet minus, is indeed this 30 foot-pounds carried over from before. But then we apply for an additional 40 foot-pounds as we pass through x equals 4 feet. So 4 feet on the plus side, just a bit past 4 feet, is going to be our previous plus the impact of what was applied on the point moment. So thinking about this from the sign standpoint of what this moment being delivered from the cut section would have to be. If this moment had to be 30 foot-pounds to keep this portion of the beam in static equilibrium back here, now I'm applying another 40 foot-pounds. And it's being applied in the counterclockwise direction. So what that's actually doing is reducing or it's counteracting the amount that's having to be applied here. So this moment here is actually opposing a clockwise net moment in the left-handmost side of the beam. Well, now we applied 40 foot-pounds counterclockwise. So this one only has to apply 10 foot-pounds now, and it goes in the other direction. So we have effectively more than compensated for the 30 foot-pounds we needed to apply here, and now it actually has to switch direction as well as it drops in magnitude. So rather than being 30 foot-pounds just picking up from the end of the other section, it's 30 foot-pounds plus the effect of the point moment, which means that in reality our lower limit of integration for dm becomes -10. So we have m sub x minus a -10. So you can see that here. The other side's a straightforward integration, and this ends up moving over to the other side, combining with constants, and so we get an expression for m at any x within that last interval of being -5 pounds per foot, x squared, nice parabola, concave down. And if we put in x equals 8 feet, we get 0, which is great because we only had a roller ball on the end. So concave down, parabolic moment, probably coming up from a negative number and reaching an exact 0 point at 8 feet. And in that same section we have shear, linearly related to x. So we could, if we wanted, use this expression over its interval of applicability and this, and then these ones, and we could find out when m and v were maxima over the entire original beam and find our maxima points. Okay. One more example where we will do a little shortcut where we'll do a graphical way of representing shear and bending moment based on end limits, types of functions, and the relationship between the two functions based on our integral relationship for polynomials. So we have another beam. We're going to have beams for all of these until we get to centroid. Hinge support at A, and roller ball support at B, and then the beam continues past B, and we have a distributed load that picks up and it's hanging off the unsupported end, plus a couple of point loads. So the objective was to find the shear and bending moment distributions. So we could do this algebraically with calculus and doing some integrals and finding moments and shears as a function of x. We can also do this graphically, or a bit of both, and it's good to check using one and the other. But either way we go, we have to start with the support reactions. So we'll condense that distributed load into 1,000 foot-pounds applied 2.5 feet from the end, and then crank through our sum of the forces in the y and sum of the moments about A. We'll get our support reactions here. It's real standard. I get both of them positive. Okay. And we're going to do a little intuition. So we're going to write, I'm going to scale this out so you can see it a little bit better. So we're going to establish three function axes, one for distributed load Q of x on the top going out, and then one for shear, and its origin is here going out, and one for moment, and these are not exactly to scale. So we're going to start by writing Q of x based on what we can see in our FBD or original schematic. There's no distributed load until we get to B, and at that point it's 200 pounds per foot. So here it is. Now we're going to write graphically based on this plus what we know about the support reactions and the applied loads. We're just going to do in our heads what the shear force is. So if the support reaction is giving 300 pounds here, we know that all along here the shear force coming from the remainder of the beam has to be a negative 300 pounds. So we can draw a line negative 300 pounds. Then when we add a 500 pound downward distributed load, the shear is going to shift up to basically balance the forces in the y at that point. So it's going to shoot up by 500 pounds. And so it's going to stay at a constant 200 until we get to this point, and it's going to shift upward again by 350 to balance the new load. So now it'll be at 550 until we get to point B effectively. Okay, then we've got two things that happen. One is we've got a huge upward point load coming from roller ball B. So at just past that, but before we've actually really picked up anything from the distributed load, the shear force is going to shoot way down negative just to balance the support reaction at A, the support reaction at B, and these 2 point loads. So just past B, our shear is actually going to be the 550 minus 1550. So it's going to plunge to a negative 1,000 pounds. And from that point to the end, which we know has to be 0, it should be linear with a slope equal to the magnitude of the distributed load. So the slope of this line equation is the same as the level of the distributed load here. So this will be 200x, and then we'll figure out our B based on what it would have to be to start at negative 100 and end up at x equals 0, or excuse me, at V equals 0 at x equals 4, 6, 12, 17. Or we could just define it by itself on this interval as 200x minus 1,000. And that's locally defined, not defined with respect to the origin. But we do know it's a line equation that ends at 0. So if we want to look at the corresponding moment without going through a whole lot of calculus, we could use the relationship between M and V and know that, well, okay, if Q is basically the slope of V, V is the slope of M. So these are all polynomials, so I can basically take the integral of this function kind of graphically, knowing that this is a constant. So the integral of a constant of negative 300 is going to be some line with a slope of 300x. 300, so it's 300x, and I know that the moment is 0 at the hinge support, so it starts at 0. So this line equation is actually just 300x, and it goes up to this point, and then it's not going to take a step function because I didn't apply a point moment, I applied a point load. But if the shear changed from negative 300 to 200, then my moment slope, which is the integral of our shear, my slope's going to change from 300 to negative 200. So you see it's shallowed out but going in the opposite direction. And then at this point, the shear goes from 200 to 550, so the slope of the moment line equation goes from a negative 200 to a negative 550, so it plunges downward. So there's a point right here in the middle where the moment is 0. Kind of interesting. So it's going to continue on a line until we get to that support B, and now we've got a huge step function in shear, but no step function in moment. We didn't apply a point moment. We didn't apply a point twist. But due to the distributed load going forward, we're going to have a parabola with coefficients and signs that are basically the opposite of these, with this being the first derivative of that. So we have basically 200x minus 1,000. If we integrate that, we've got a kind of a concave downward parabola that's going to approach that 0 point at the end, kind of asymptotically, more or less. Not quite an asymptote, but looking like it, because we can't support any moment out there. So the limits of integration from our algebraic solution up here effectively just become the handoff points to connect these curves on the graphical method. But this is a very easy way of finding maxima and minima. If I were just trolling effectively for where's my maximum shear, it's real easy, especially if you draw these to scale. And if I wanted to know my maximum moment, I'd be looking at either this point or this point, and probably looking at both of them as being pretty big. So this graphical method of expressing shear, distributed load, and bending moment based on different regions of loading in the beam, handshakes at the limits, at the endpoints of these regions, and then most fundamentally, the sign and the integral derivative relationships between these functions really gives you a lot of insight on a kind of a gut level of what's going on, and it serves as a super valuable check of your algebra calculus method if you do both together. So that is it for this lecture, and I hope you can see that even though there are a lot of different valid ways of approaching these shear and bending type of solutions, the definite integral, I think anyway, is the easiest and most bomb-proof, where you write the relationships between your distributed load and your shear, or your shear and your moment as these indefinite, as differential expressions, and then just integrate each differential and use that fundamental theorem of calculus on one side, and then use that lower limit to roll in both the endpoint of the previous section adjusted for any points that you pick up as you head into the next section. This is a lot easier than keeping track of resultant equivalent forces and whatnot that we saw in the previous lecture. They're both valid. If done properly, they can both get you there. This one, in my opinion, is a little bit easier, and certainly the graphical method can be deployed in conjunction with anything or as an initial estimate, especially for a simple system where you have a lot of constants and line equations that can kind of be integrated in your head.